Okay, our next speaker is again Monika, Dr. Manika Maharjan. And Dr. Maharjan has a PhD in civil engineering at Tokyo Institute of Technology in Japan in March 2015. So her research interests are in the field of earthquake engineering, which includes seismic design, soil liquefaction, and its mitigation, ground motion interpretation, and soil structure interaction. And currently she is involved in the design of Hinkley Point C nuclear power plants as a geotechnical engineer. So and she's talking about also, I think, soil liquefaction during April 25th, Gorkha earthquake, Nepal consequences.
My name is Manika Maharjan. I'm working as the geotechnical engineer at Atkins Limited. So basically today I'm sharing some of my findings from the reconnaissance survey that I conducted after the Nepal earthquake. And I'm going to talk about the soil liquefaction during April 25 Gorkha earthquake and its consequences. So I know these technical terms like liquefaction, earthquake, these terms might not be very familiar with many of us. So I'll try to keep it as simple as possible. A big background about myself. I received PhD in geotechnical earthquake engineering from Japan, from Tokyo Tech, from Japan in March 2015. And I was supposed to join my job in UK from early May 2015. But I was in Japan when earthquake occurred. And I thought this might be a very good opportunity for me to go back and do some damage assessment. So I postponed my job for 2 months and I went back to Nepal. And I had a chance to do the reconnaissance survey with the Geotechnical Extreme Event Reconnaissance GEAR team from US. So GEAR is an association sponsored by the National Science Foundation, which dispatches its team of expertise to the disaster hit area. And they dispatch a group of the team from different universities like the University of California, Berkeley, and the San Diego and Virginia Tech. A team of expertise came to Nepal on May 5, and I had an opportunity to do the damage assessment with them. After the earthquake, I have also worked as a curator. That means I used to write a blog about the geotechnical impacts caused by Gorkha earthquake section on the EERI clearinghouse. So EERI is also an association in US. And prior to that, I was a team member of the reconnaissance team to investigate an earlier event, that is the Nepal Sikkim earthquake, which occurred in September 2011. So this is the background of my presentation. I'll start with the background of the earthquake, followed by the characteristic of April 25 earthquake and its consequences, and liquefaction in Kathmandu Valley, the Basin age effects, and the summary. So I'll start by describing a background about the earthquakes. So we all know what earthquake is. I'm just taking you back to the high school level. So, normally, the earth has the many blocks, which we call as a plate. And we can see in this figure, these are the plates or the blocks. So when two blocks of earth cross, suddenly slip one another or move relative to each other, earthquake occurs. And during this rupture, a huge mass of energy is released, which creates the vibration called the seismic waves, and that radiate up through the earth crust to the earth's surface, causing the ground to shake. Here we can see this is the rupture point, and the energy is propagated from that center, and we call this center as the hypocenter. And the point above this hypocenter on the ground surface is called epicenter. And normally the seismic waves are of two types, the body wave and surface wave. So in this video you can see when earthquake occurs, the body wave travel through the body of the earth, and surface wave travel from epicenter across the surface of the earth. So the name itself defines the meaning. So body wave travels through the body and surface wave travels through the surface of the earth. So body wave are of two types, P wave and S wave. So P wave is the first one to feel here when earthquake occurs. The P wave is the first wave to feel, and P wave travel in the direction parallel to the wave, and it moves the building in horizontal direction. So that's the one to first that we feel. And after that, the S wave, and S wave travels in a perpendicular to the wave motion, and it moves the building in horizontal direction. So similarly, the surface wave moves the direction also in the horizontal direction, and the surface wave is responsible for most of the damage and most of the movements and shaking that we feel. And this is the plate tectonics of the Earth. So there are many plates in Earth, and Nepal lies on the boundary between the Indian plate and the Eurasian tectonic plate, as shown here. So here's the Nepal, this is Indian plate, and this is the Eurasian plate. And so these two plates are moving against each other at the rate of about 45 millimeter per year, and this collision lifted a part of the land which forms the Himalaya. So that's why we have the large number of mountains and Himalayas. And during this collision, a huge mass of energy is accumulated inside this subduction. And so this collision caused the April 25 earthquake. And the boundary between this region has a long history of the great and the large earthquake in the past, which makes this area one of the high seismic hazard regions in the world. So the biggest one in the history of Nepal is 1505 earthquake of magnitude, I guess is about 8.3 at that time, which killed about 30% of the Nepal's population. And later, the 1934 earthquake, which we call Nepal-Bihar earthquake, it killed about 10,000 people and damages about, I think, 30% of the houses in Kathmandu Valley. So this area is a very highly seismic region, and whole Nepal lies in this zone. And these are some of the earthquake faults in Nepal. So we have many faults caused by this collision, the subduction between the Indian plate and the Eurasian plate. We have the MFT, that is the main frontal thrust, and MBT, that is the main boundary thrust, MCT, the main central thrust. So this earthquake, the Gorkha earthquake, ruptured near the main Himalayan thrust, as seen here. And so on April 25, 2015, a magnitude of earthquake 7.8 occurred around 80 kilometers west of Kathmandu in a Gorkha district, the Barpak area, with the focal length of about 8.2 meter. And the rupture area, like the rupture was about 120 kilometers by length and 80 kilometers by width. And the peak slip, the displacement caused by the earthquake, was about 4 meter, more than 4 meter. And from this figure, we can see the earthquake occurred at this region, but the whole damage, that is the earthquake, propagated only towards the east, that is towards the Kathmandu Valley. So the wave did not propagate around the western part. That's why we didn't see any damage in Pokhara, for example. Like Pokhara and Kathmandu both are situated at about 80 kilometers from the epicenter area, but the damage was concentrated only in Kathmandu. And so till date, as of the May 6, 2016, according to the Nepal Seismological Center, about 456 aftershock has occurred around this region, and the biggest aftershock was the magnitude 7.3 in Kodari. So I'll talk a bit of the characteristic of the April 25 earthquake. So normally we measure earthquake in terms of acceleration, that is when there is an earthquake, so the seismogram records the movement. And this earthquake has the maximum acceleration of about 0.16 g. G is the gravity, that is 9.81 meter per second square. And this PGA of about, we call it PGA, that is peak ground acceleration. This PGA is about very low for such big earthquake. Normally we assume like a 0.3 g, 0.4 g. Even in Japan earthquake, when the magnitude was about 9, there had been a PGA of about more than 1G, but in Nepal earthquake it's very low, 0.16 G for such a big earthquake. So it has been a surprising factor for all the scientists and researchers from all over the world. So why we have such a very low PGA, and this might be, the good thing for us as well, and that's why we don't have much destruction in Nepal. The answer might be Kathmandu Valley was a ball of the ancient lake bed deposits, as shown here. It has a 500-meter deep clay deposits, and something about this valley has dampened the shaking. That's why we have low PGA. And this shows the spectra of the earthquake. This means the behavior of the earthquake. So the peak value is for the 5 period time second. And normally this type of earthquake, which has the time period of 5 seconds, it causes damage to the high scraper building of about 40 to 50 story. It means for the very tall buildings, for example, this is a very tall building, and during the free vibration, it takes about 5 seconds to come back to complete the one cycle, 5 seconds. So the natural time period of this tall building, high scraper building, and this earthquake is nearly the same. That means this earthquake is for the tall buildings, not for the short buildings. And whereas for the 10-story building, the natural time period is about 1 second. And for the residential buildings such as 2-story and 3-story where we live, the natural time period is just 0.2 seconds. So we observe very less damage in Nepal because we don't have much high-story buildings. And this earthquake has caused a huge impact in Nepal with the casualties of about 9,000 and the economic loss of about $7 billion US. And apart from the casualties, we have the huge cultural loss, building damage, and the geotechnical failures as well. And this shows the cultural loss. Our heritages, the landmarks, monuments has been completely or partially destroyed. And apart from that, the structural failure is the significant failure from the Nepal earthquake. About 500,000 buildings were completely collapsed, and about 250,000 buildings were partially damaged. And also the landslide has been triggered due to the strong shaking. And basically the landslide are in the form of the rock fall. Here you can see the rock is falling and hitting the building. And this photo was taken in the Sindhu Palsuk district, and this was in the Barabisi. So at this time, I was here when the second aftershock of about 7.3 occurred, and this rock was fallen from that aftershock. And also this shows the landslide area that blocked the road, and this is the active landslide due to the aftershock on May 12 earthquake. And we have a lot of damage in the roads and highways as well. This is the newly constructed Kausaltar-Lokanthali road section of Ornico Highway. Here we can see the large displacement and many cracks in the highways. And we have the liquefaction as well. This is in the Rampur area. And liquefaction was observed during 1934 earthquake as well. Here we can see the cracks in Turikel. So what is soil liquefaction? It's a completely technical term, so let me explain in a very simple way. So soil liquefaction occurs in saturated soil. The saturated soil means, for example, let's see, this is the soil particle, and the gap between the soil particle is completely filled with water. So there are many soils or sand, and the gap is completely filled with water. This is the saturated soil. And normally this shows the stress. That is, the stress of this soil increases towards the depth. It's just very simple physics, high school physics. And there exists a contact force between the soil, just between the soil, and that we call as the effective stress. Normally, the load of the superstructure, that is, we have the building and the foundation lies on the soil. So the load of the building is carried by both the soil and water by combining the bearing capacity of both soil and water. And so during earthquake, what happens? During earthquake, these soil particles move away from each other, so it loses its contact forces between each other. So the whole load is transferred to water, and as a result, pore water pressure increases. That is, soil can no more bear the load, and the load is transferred to water, and this whole soil ground behaves like a liquid or like a fluid, as seen here. And this video is from the Japan earthquake. Like the soil liquefaction occurs, and then the soil and water combines to form the water, and this water comes out onto the ground surface through these cracks. And it is very vulnerable and one of the factors for the damage during earthquakes. So this phase is called liquefaction. And this shows the tilting of the building during 1964 Niigata earthquake due to loss of bearing capacity by soil liquefaction. And this shows the sand balls during 1989 Loma Prieta earthquake. And this shows the damage to the port facilities during 1995 Kobe earthquake. And this is the damage to the dams during 1999 Chichi earthquake in Taiwan. So let's move to the geology of the Kathmandu Valley. So as I've already mentioned, Kathmandu Valley was once a big lake with a 500 meter of the deposits. And this shows the cross section, what's inside the Kathmandu Valley. That is the cross section of the ground. And this the northern part near the Sundarizal area. So it consists of the sand, the mixture of the sand and gravels and the boulders. Whereas the central part and the southern part consists of the thick layer of the black cotton soil, which we locally call as the Kalimati. And this shows the liquefaction potential map of Kathmandu Valley. This map shows which area has the high potential for liquefaction during earthquake. And this map was from PIA 2003, so it's a long time ago. So it shows that the central part, this red one, is highly susceptible to liquefaction. And also because of these rivers, normally near the river we find sand. So sand is, normally liquefaction occurs in sand, so these areas are highly potential places for liquefaction. And basically there are three conditions for liquefaction. One is groundwater table, because liquefaction occurs only in saturated ground. And other is the loose sand, and third one is the strong ground shaking. The earthquakes would be pretty higher. And when this map was prepared, the water table was about 5 to 9 meters below the ground surface in the northeastern part, and about 2 meters in the central and eastern part, and 1 meter in the southern part. And the water table was pretty higher a long time ago. And these are the liquefied sites that I observed from my survey. We started from the Mudpani, Duakot, and then Guheswari, Lokanthali in Bhaktapur district, and Imado, Hatiban, and Bungamati in Lalitpur district, and Ramkot and Manamaizu in Kathmandu district. So the Lokanthali section, Lokanthali has been an interesting failure for it has attracted many researchers from all over the world. And we observed the vertical displacement settlement of about 1.3 meter and the horizontal offset of about 0.4 meter. So the question is, why did it occur? What might be the reason behind this? What is the mechanism for this failure? So it might be due to the lateral spreading. So it's again the technical term. So lateral spreading occurs in the gentle sloping area near the river. So here is the Monara River, and the Lokanthali lies in the very gentle sloping area. So what really happens during lateral spreading? For example, this is the Lokanthali area, this is river, and in this area, this is the saturated sand which has the potential to get liquefied. And during earthquake, this area liquefies and it decreases the strength and stiffness of the soil. And as a result, the upper part moves towards the riverside, that is free surface. So lateral spreading is the process of lateral moving of the blocks or the ground towards the free surface. So because as this layer, this part moves towards the creek, that is the river, and we observe the deformation, displacement and deformation in the pavements. And this shows the sand balls in the Duakot and Mulpani area. So sand ball is the sand and the water coming out onto the ground surface. So this shows the mechanism. So here the liquefaction occurs and it ruptures as a volcano. And again, we observe the sand balls in the Manamaizu place, and also there is the lateral spreading that causes the building to tilt about around 15 to 20 centimeter. And there was a massive sand ball in the Ramkot area, and according to the locals, the sand ball occurred for about 24 hours even after the earthquake has stopped. And so the question is why and we can see the liquefaction occurred, liquefaction occurred around the basin edges only. There is no liquefaction in the interior part of the Kathmandu. The question is why. The convincing factor might be the basin edge effect. So I'm going to talk it next slide. And the other factor is now the ground water table has decreased drastically in Kathmandu Valley. So before it was just 2 to 3 meters below the ground surface. Now, according to the latest article published in Himalayan Times this month, the water level has decreased about 8 meters in these 5 years, I guess. So now the water table might be about 20 meters or 15 to 20 meters. That's why we didn't see liquefaction in the interior part of the Kathmandu Valley. And we didn't have a shallow water table, and the shaking was not very strong. So the basin edge effect. So during earthquake, we have the body wave, as I explained before, this is in the horizontal layer. And whereas in the basin edge effect, so we have the body wave coming from the basin, and we have the surface wave coming from the edges. So there occurs the constructive interference between the body wave traveling from the basin and surface wave traveling from the basin edges, and which increases the amplitude of the shaking. That's why the deformation are more towards the edges, like we can see in Sitapaila, Balaju area, and most of the buildings were collapsed. I think this might be the convincing reason for that. So to wrap up, the continuous collision of Indian and Eurasian plate caused the Gorkha earthquake, and we had the huge economic loss to the infrastructure. And we observed the geological failures in the form of landslides, slope failures, rockfalls, and liquefaction. And also the location of the ground failure was limited only to the edges of the Kathmandu Basin, and this is due to the basin edge effect. And the low intensity shaking and low groundwater table localizes the liquefaction only to the limited area. And further studies are required so to obtain the soil profile or the damping curve of this black cotton soil, and also we need to interpret the ground motion so that we can have the good conclusion and we can learn from this earthquake. Yeah, that's all. Thank you very much. Any questions?
I think we don't have time for the question, but one quick question. Okay.
Yeah,
Okay. Yes.
So the interesting thing is, like, we're in 21st century, and we have pretty much forecasting for all the other things, events happen, right? So why we cannot forecast the?
Well, it's a very difficult question. Yeah, you're right. Like in this 21st century, we have been able to predict many things, but still now, till date, we are not able to predict the earthquake. Right, you're right. I don't have answer for that question. I'm not a seismologist. I'm just an engineer. Yeah, we cannot predict the earthquake, but maybe someday in some future we may be able. I hope so.
I think just a quick comment. I think prediction is the most difficult thing to do in this world, whether it's 21st or 22nd century. We've been doing this seminar for the third year now. We couldn't predict how many people are coming to.
Okay.
Exactly, it's a very difficult question. I cannot answer that when and how.
Thank you, Manika, once
Thank you.
again.
Pleasure.